Welcome to part 3 of week 3 of AP Stats. Hello. Alright, so again, we're going to have to do some pretending because I can't actually give you candy, sadly. So pretend that in each group of 4, there was a random sample of 50 Hershey's Kisses to bring back to your desks. Each group was going to toss the 50 kisses and then calculate the proportion that land flat. P hat would be the proportion of the sample kisses that landed flat. All right, so question 1, what is your point estimate for the true proportion that landed flat? Looks like I forgot to put in my yellow box there, but let's pretend that 21 of the kisses landed flat. So your proportion here would be 21 out of 50, which is 0.42. So go ahead and put that in even though there's no box for it. All right, take a moment to try to answer questions 2 and 3, and then hit play when you're ready to go over those. All right, so our population is going to be all Hershey's Kisses. Parameter would be the true proportion that lands flat. The sample is the 50 kisses that each group has, pretend. And our statistic, P hat, is 0.42. All right, is this a random sample? Yes, it says that somewhere. There we go. And what that means is we can generalize. Blast from the past here, but if we are taking random samples, that means we can make statements about the broader population. Okay. So that's important. We're going to come back to that idea. Questions 4 and 5, I'm just going to give you, they're like in your notes somewhere, but I don't need you to like go shuffle through and find all those. So the formula for calculating the standard deviation of the sampling distribution for P hat is big square root P 1 minus P all over N. Okay, and then for question 5, I'm going to walk you through that as well. Looks like I didn't actually screenshot the question, but it's asking you what condition must be met. The 10% condition. And has it been met? Yeah. 50 is less than 1/10 of all Hershey's Kisses. So I'm just going to give that a big check mark. Yep, we got it. Okay, so now question 6. We don't actually know the value of P. That's the whole point of a confidence interval. We don't know like what's the true proportion that would land flat out of every single Hershey's Kiss. So we're going to use P hat instead. I want you to use the formula I gave you for question 4. And I want you to plug in your value for P hat to calculate the standard deviation. Pause while you're working on that and then hit play when you're ready. All right, so if we are finding the standard deviation here, it's going to be big square root, but now it's going to be P hat, 1 minus P hat, all over N. The P hat that we got was 0.42. 1 minus that is 0.58. Sample size was 50. And if you're doing all that right, you should get 0.0698. Okay, for question 7, is it appropriate to use a normal distribution to model the sampling distribution of P hat? Justify your answer. For this, we're looking for whether it meets the large counts condition. And as a reminder, that means that we would expect to have at least 10 successes, and we would expect to have at least 10 failures. So let's check this out. I'm going to do N times P hat. That's going to give me my number of successes. And N times 1 minus P hat. That gives me my number of failures. So my sample size is 50. I'm expecting, based off of my sample, that 42% of them will land flat. So that gives me 21, which is greater than or equal to 10. Yay. And then for my failures, 50 times 0.58 is going to give me 29. That is also greater than or equal to 10. Yay. So because both of those numbers, my number of expected successes and my number of expected failures, are greater than 10, we can go ahead and say yes to the question of, is it appropriate to use a normal distribution? All right. So we need to talk about normal distributions. They're sort of coming back. You probably noticed we didn't talk about them for a while, but here they are. In a normal distribution, 95% of your data lies within 2 standard deviations of the mean. This value is called the critical value. How many standard deviations of the mean goes within it, connects to a certain percentage. I'm going to show you how to do this using inverse normal on your calculators. Unfortunately, Apple doesn't let you use fake TI stuff because they, intellectual property and stuff. So I can't actually show you on my iPad. Well, I guess maybe I could. Let's do it. I'll switch over I'll find my little testing calculator. Okay, so we're looking for 80% here. So I'm going to walk us through how to find that. Before I jump to that though, I'm going to make a quick picture. So I'm trying to figure out what value would work to give me 80% of my data, like right here. So notice that there's a little tail here that's not filled in, and there's a little tail here that's not filled in. Before I jump to the calculator, we got to talk about this. So this is 80 in here. 80%. That means that this has to be 10 and this has to be 10. It's a common mistake to think that the other part has to be 20, but if you think about it, it's split into 2. So total, yes, it equals 100, but the big part is 80, and then on the sides, that means I have to have 10 on the left and 10 on the right. So remember that number, that 10, and then we'll go find my bootleg testing calculator that I like. All right, cool. So in order to go to inverse normal, you're going to go to second vars to get to your distribution menu. We've been using a lot of the CDFs and PDFs in this menu. We have not used inverse normal for quite some time. So we're going to go to inverse normal. My calculator, my real calculator, does not have that last option. So bear with me while I try to figure this out. Mine and probably yours, it just asks for area, mean, and standard deviation. For area, I'm going to put in 10%, 0.1. And then I'm going to keep the mean at 0, standard deviation at 1. I'm just going to try not messing with the tail thing. I don't know what that's about. Let's see, a left tail. I think on a real calculator, I think this gives you a positive value. Let me just check something. 0.1. Oh, no, it gives us a negative. That's fine. All right. So we're getting negative 0.1282. Okay, yeah, no, I understand that. That makes sense. So remember that number, negative 1.28, and then I will go back and I'll jump back to my slides. So what that tells us is that the z-score right here is negative 1.28. And that's for us to be able to get this 10% number. What I can do though is I can just turn that positive, and that's why I was confused for a sec. Because we're looking at sort of both sides on this, we're looking at the left and the right, this statement now makes sense. It says 80% of the data lies within 1.28 standard deviations of the mean. So that means that, let's see, here's my mean. This part on the left is if you subtract 1.28 from the mean. This part on the right is if you're adding 1.28 from the mean. All right, I'm going to do one more example for you, and then I want you to try the others. So I'm going to erase my little sketch I have going on down here. Sometimes the eraser just doesn't line up. The pen is really accurate, and so I don't understand why the eraser is glitchy. It's fine. right, so now we're trying to figure out how many standard deviations away from the mean would allow us to contain 90% of the data. So similar process here, but now this is 90% in the middle. That means each of these tails is 5%. We have to get up to 100, and then each of those tails, they're going to be symmetrical. So you could go to inverse normal and type in 0.05 for the area. I can do that again. So second vars, there we go, 0.05. And then just keep those numbers at 0 and 1. You probably don't have that tail business, so don't worry about that. And then let's see, I'm getting 1.65 if I'm rounding. So that's what I'm going to put right here. Go ahead, pause. I want you to try to calculate the last two, and then we'll go over those in a sec. All right, for C, you're going to use inverse normal, and you're going to use 0.025 for your area. That should give you 1.96. And then the last one, if it's 99%, your area there would be 0.005, I think. Basically what you're doing is you're subtracting it from 1, so 1 minus 9.99, and then dividing that by 2. Yes, I just wanted to make sure my decimal points were in the right place. And if you're doing that, you should be getting 2.58. All right, question 9. Calculate the margin of error for a 95% interval by multiplying the critical value and standard deviation that you found. So one thing that we will put in our notes that would probably help you with this is that the margin of error, let's see, do I just want to put this in our notes right now? Yeah, okay, no, I don't want to just yet. It kind of tells you what to do. You're going to be multiplying the critical value and the standard deviation that you found. Okay, so for a 95% confidence interval, we're going to be looking back at this number, 1.96. So I'm going to do 1.96, that's my critical value. And then we already calculated the standard deviation. It was 0.0698, and that was from question 6. When we're doing that, we get 0.137. Okay, from here, I want you to actually find your interval. So you're going to use your point estimate, which was 0.42. And then you're going to add or subtract your margin of error, which was 0.137. When we do that, actually go ahead and try to calculate that and then click play when you're ready. Okay, when you do that, so first of all, I'm going to do 0.42 minus this number. That's going to give me my lower bound, so 0.283. And then I'm going to do 0.42 plus this number to give me my upper bound of 0.557. All right, so with questions 11 and 12, I forgot to edit these for our little for our context right now. Add your interval to the graph on the board. We don't have a graph on the board. We can just go ahead and skip these. That's all right. Because without the graph, you can't really answer question 12. It's fine though. Okay, so we're gonna go over some notes. There's kind of a lot to go through here, and then we'll do our check for understanding. So when you are checking for conditions, there are 3 conditions to check. First of all, we have to check that it's random. Second of all, we need to check the 10% condition. And just as a reminder, that means that your sample is less than 1/10 of your total population. And then we also have to check for normal. And the way that we do that is using large counts. As a reminder, what that means is that your expected number of successes is greater than or equal to 10, and your expected number of failures greater than or equal to 10. Okay, next thing to talk about is critical values. That's what we were finding using inverse normal on the calculator. A few common ones, and these just might come in handy. For 90%, the critical value, which I write as Z star, is 1.645. For 95%, the critical value is 1.960. For 99%, your critical value is 2.576. So these are just like handy. These might, if you have these written down somewhere, you just won't have to like use inverse normal every single time. But say I want you to find some random confidence interval, like an 82% confidence level or something. What you're going to do is you're going to find, you can use inverse normal, and then the area to find that, you take 1 minus your confidence percentage and divide that by 2. You could also, like if what I was doing with my little sketches made sense for you, like if I do have like a 80%, that means this is 10 and this is 10, you're going to plug in 0.10 there. All right, and then the last thing with notes on this is the formula for calculating and constructing your confidence interval for a proportion. This is a big equation, so I actually want to insert another page here. Okay, so formula for confidence interval for a proportion. Okay, so what you're going to do, first of all, basically like the main idea is that it's your point estimate plus or minus your margin of error, but I'm going to show you how you can actually calculate all that stuff. So that's your general formula that we're using, but the specific one where you can actually like plug stuff in, it's your point estimate, so whatever your sample proportion was, plus or minus. Then you have to find your critical value. Then you're going to multiply it by a big old thing. Your point estimate, 1 minus your point estimate, and then the denominator is just your sample size. Okay, so with that, I want to give you some time to work through your check for understanding. When you're ready to go over it, hit play. All right, so identifying the parameter of interest. Parameter, remember, that describes your population. So P here is equal to the true proportion of kids who want to be a doctor. Checking our conditions, if we can even make a confidence interval. So there's 3 conditions to check. Random, let's see. Yep, we got it. Okay. 10%. Let's see. We have a sample of 1,000. That is less than 1/10 of all kids. All right, and then for normal, we have to check for large counts. So if I have 1,000 in my sample and I've got 0.055, that's going to be my my probability of a success. That's 55 kids wanted to be a doctor, so that's more than 10. Great. And that means that the kids who don't want to be a doctor are all the other kids, the 945. That's also greater than or equal to 10. Great. Okay. Finding the critical value for a 98% confidence level. So we can use inverse normal here. I don't think I told you 98 in my handy ones. Nope. Okay. If we're looking for 98%, excuse my really ugly normal curve here, that means that each of the tails is going to be 1%. So if I'm doing inverse normal, my area will be 0.01. Okay, but now I have to plug this into that big old equation. I'm actually going to do it over here just so that we can look at it and also have more space. So this is check for understanding part C. All right, so first of all, we're going to take our point estimate. That in this problem is 0.055. 5.5% of kids want to be a doctor. Okay, and then I'm going to add and subtract. I just found my critical value. Oh no, I didn't actually find it yet. It should be 2.33 if you do the inverse normal. And then inside my square root, it's going to be 0.055 times 0.945 all over my sample size, which was 1,000. And when you do that and get your lower and upper bound, you should be getting 0.038 for your lower and 0.072 for your upper. And then the last part is to interpret in context. We are 98% confident that the interval from 0.038 to 0.072 contains the true proportion of kids who want to be a doctor. All right, part 3 is done.